So let me share my screen. You can see the book. Today we will be talking about policy gradient methods, and that's something different from what we have discussed so far in the book, and we will also see that to some extent there is similarity and a way to merge the policy gradient methods with value-based methods. So let's get to it. So far we were trying to learn some value function. Usually it was like action value function if we wanted to produce some control, but there is another way to approach the problem, and what we can do, we can define some function that is a parameterized policy. So basically our function will output a probability of an action given a state, rather than producing the value for a certain state or state action pair. And in this way, we can get certain advantages as well as certain disadvantages. So to make this work, we need to define some differentiable objective function. So that would be some function that is parameterized by parameter vector theta, and it should produce a single scalar that is a measure of the performance of agent in the environment. And by applying the gradient of that function, we could update our parameter, and as we will see, we can improve the performance. And we will also discuss some ways to incorporate the value function into this framework, and that would be actor-critic methods, where actor is our policy. So that would be like a network that provides a policy for us, and a critic would be the value function. So that's something that measures the value of states or state or action values. So let's get to some details. So first, let's discuss some motivation behind using the policy approximation rather than value approximation, and like try to figure out in what cases this might be beneficial. So first of all, how would we parameterize the policy in this case? So one way to get, so what we want to get from our function is a distribution of probabilities of actions given a state. The most common way to get a distribution from some like logics underline is to apply a softmax. Probably if you are used to like supervised learning, you know this expression very well. And in this case, our policy would be parameterized by softmax, where in the nominator we have an exponential of this H, which represents the preferences. So in this case, the this function H provides us some numeric preferences, which can be arbitrary numbers, and we want to turn them into the proper distribution, so that sums to 1. Therefore, we can exponentiate those numbers and normalize them by the sum of the exponential over all possible actions. That would give us the proper probability distribution, and the exponentiation gives us some way to kind of exaggerate the most useful actions and weigh down the least useful actions. And also this exponentiation plays well with a logarithm, and that is useful, as we shall see later. And also we can use temperatures of max, so we can add here hyperparameter, which would be so-called temperature, if we want to smoothen out this distribution a bit. And also another intuition to have when you think about softmax is that it is a kind of soft approximation to the argmax. So we want to get the argument that maximizes this function, but instead of getting like 1 and at one position and 0 everywhere else, we will have a softer version of it, where some like more the actions that have higher preference would have higher values, and the action with lower preferences will have lower values. But this is a smooth function and a differentiable function, unlike the argmax, which is kind of hard, and the gradient is 0 everywhere except for the maximizing argument, right? Okay, so about this preference, it can be any kind of function. It can be a linear function, as shown in equation 13.3, but also it can be the artificial neural network, and yeah, so that can be arbitrary complex function, and by applying the softmax at the output, we get this probability distribution at that. Those are kind of two independent ideas, and we have like free choice of what the function h could be. But like simple linear function is the most easy to analyze choice, so we will stick to that during this discussion in the book. And to give some motivation why having this parameterized policy, which can produce the action probabilities rather than just a single best action. Let's consider this example, 13.1, the short corridor with switched action. We have a very simple like Markovian process, a grid world, which with one simple twist. So in state 1 and 3, we have like by moving left, we move left, and by moving right, we move right, as you would expect. But in the second state, we have that switch, like a twisted. So we, by applying like a right action, we will actually move left, and vice versa. And that makes the greedy policy obsolete. So you can easily imagine by applying like when you have action values and you have to mention why this why we have problems here. So we have this particular assumption that all the states have the same representation here. So we will have a feature vector 1, 0 for the right action and 0, 1 for the left action for all states. So for our learning agents, these states are effectively indistinguishable. And this is kind of like strange assumption to make, and it makes this example a bit less of I don't know, useful, I guess, but we will also see another example which I think makes it more interesting. And if you watched the DeepMind lecture, that I mean that one from the video lecture from DeepMind. But let's get through this one. So you can see that if we select a greedy action, we will essentially never complete a single episode, because the greedy actions assume that we will select a single action left or right for each state, and assume that we select right always, as we want to move from the state 1 to state 2. But then the right action will move us back to state 1. So we are stuck with this infinite loop here. And by selecting always left action, we obviously never leave the state 1. So that's even worse, or not worse, but just equally bad. That's infinite loop. We never complete a single episode. By making the strategy epsilon greedy, that is another way to produce a strategy from the action values as we in previous chapters. We can complete an episode, but you can see on this plot here that both epsilon greedy action selection is like really bad compared to the optimal policy. So in both cases, it will take much longer to complete a single episode compared to some like in-between strategy here. And it can kind of easily be understood intuitively by extending this logic applied to the extreme cases, right? But so basically, when we act epsilon greedily, moving right, it will take quite a long time before we can take a left action while in state 2 to switch to the third state and eventually get to the goal. All right, so, and the optimal strategy here would be something in between with just a slight preference towards moving right. And by adopting that strategy, we can actually get to much higher score. And you can see that there is some kind of flat surface here. So around that number, so around like between 0.5 and 0.6, we have quite a flat loss surface, and our objective is way much better compared to any like extreme choice of epsilon greedy strategies. Okay, so how do we find this stochastic strategy? Yeah, let's just before we get to that, the policy gradient theorem, and let's have a brief look to the exercise 13.1. So we can essentially solve this problem analytically to find this number here, and this can be done. I will just briefly go over that. We can write out the values for each state. Here it will produce us the system of linear equations. And that is quite straightforward. That is what we have probably discussed some time ago. So you can basically solve this grid world by formulating a system of linear equations, recursively defining each state in terms of the other states. Then we can solve, we can express the value for the initial state in terms of probability of moving right. That will give us the simple linear, like algebraic manipulations applied to this system of equations will give us this form for value of state one. Then we, to find the best probability, we should find the value of p that maximizes this function here. So we can compute the derivative for v1 with respect to p and solve this gives us basically a quadratic equation subjected to some constraints. And also you can see here that we will have no solution if p equals to 0 or 1. Judging by this denominator, and that makes sense as I mentioned before, by making the probability like of moving right 0, which means always move left, or 1, which means always move right. We never complete a single episode, and basically we have negative infinity for value of state 1. So that should be like that should make sense as well. And we can solve this, that gives us some particular value here. And we have the associated V star for that strategy, which is around negative 11.6. So yeah, that's a solution for this process. Now I would also like to just to consider another example. So that kind of makes more sense to me because the assumptions are less ridiculous. So in the previous example, we had that assumption that each state is indistinguishable. For us, that makes the state representation really the choice of features to represent the states really bad choice, and that kind of makes produces a problem for us. But we can consider another very simple example with kind of less detached from reality, I would say. So consider this simple grid world. We have 3 terminal states. The central one is associated with positive reward, and the left and right ones are associated with negative rewards here. And the states are represented by the encoding of the walls that are observed in that particular state. So imagine that, for example, that we have a robot here that can move in this grid world, and we cannot see like far away, so we cannot see what are the walls in the next room. We only can see the walls in this room where we are situated, and that would make this kind of feature representation reasonable. So we have this kind of grid world where the states are represented by the set of binary features representing walls that we can observe. Therefore, these two states shown in gray will have the same feature representation again. And as you can see from this grid world, it is not possible to provide a deterministic policy that will result in always getting to the positive reward state here in the center, because these two gray states are indistinguishable, and if the policy is deterministic, we can basically select here either move left or move right. But despite the fact that states are kind of represented in the same way, in these two states we have either move left only from this one and move right from this one. So we need some way to be able to move kind of stochastically in this state, and that is possible with some policies that is parameterized in a way that it will produce not kind of a deterministic single action, but will produce a distribution of our actions. And basically here we have in that way we can get this flexibility to set the probability of moving left and right to be equal for the gray states. And that is optimal in this case. By following this strategy, when we move from this state, we move deterministically right. From this state, we move deterministically left. Here, we move deterministically down. But in these two states, we move stochastically left or right. By following this strategy, we will always end up in the positive reward state. It will take kind of longer than if we would kind of go, if we would know for sure where to go, but still we will always get to the positive reward. So I hope this two example kind of illustrate the benefits of having a parameterized policy over having like this greedy or epsilon greedy policy, some policy determined in relying on the contrast between the state values rather than the policy itself. So from that, we can conclude that depending on the task, it is possible that the approximating policy directly can be beneficial compared to approximating state values or action values. And yeah, that is an motivation to try policy gradient approaches. Now let's discuss why the policy gradient work. And we have this policy gradient theorem, which is slightly different for episodic and continuing cases. We will discuss both cases here, but let's start with episodic one. It's a bit simpler here. So first we need some objective that depends on the parameters, and defines how good our policy is. A natural choice of this objective would be a value of a starting state. So this is kind of a very simplified case, and we can incorporate more to it. But let's say we always start in a particular non-random state as 0, and we have no discounting. So the discounting factor is equal to 1. Then we can define this objective we want to maximize as a value of a starting state. So, and that is like completely reasonable. We want to get as high reward as we can for an episode, and that objective will provide us just that. So let's now see what the gradient of this objective would be in terms of the policy we can have. So the policy in this case is a function parameterized by theta, and it has the state as its argument, and it provides a distribution of probabilities over actions. And so here is a derivation of the objective we want to follow. So if we differentiate if we find a gradient with respect to the parameters theta of the value of a state, this gives us we can kind of write out the value of a particular state as a sum over all actions of probabilities of those actions multiplied by the values, action values of those states. And then we can take the gradient, apply the product rule from calculus. We want to find a gradient of this function, and this is a product of two functions, so it will give yield us a gradient of the first function multiplied by the second one, plus the first function multiplied by gradient of a second function. And then we can keep unrolling this argument here, the q gradient of q function here. It can be written out as a sum over all possible future states and rewards, multiply and of a product of the rewards plus the value of the next state, multiplied by probability of the transitions. And we can like manipulate these expressions further and get to the sum over future states of values of the so we take gradient of value of the next state, and the transition do not depend on our policy, and therefore we can safely like take the gradient of only of the value function of the next state, because the transition is a property of our environment. So the transition probability is a property of an environment rather than of a policy. There and then we can again unroll this expression in terms of the future actions and so on. So basically you can see how this unrolling is continued. And finally, we come to writing out this as a sum over all the states, like from 0 to infinity in steps here. And we have this probability of being in state S or moving from state S to state X. and that multiplied by the sum over action of gradient. So this term here, the first term. Okay, and with that, remember that our objective is so that here we written out the gradient of value function for particular state for any state, but we are interested in a gradient of value function for starting state as 0, and now we can kind of apply the same. So we can substitute as 0 to here, and that will give us this expression that we can basically this I don't know how it's called, eta of S or whatever, is a state count. Basically, how often do we visit a state S after we started from state as 0, and then we sum over all of those states. So we can kind of rewrite that to get this mu, which is a distribution over states, that is a probability of being at state S, and summing over all of the next states, and here we get to be like, we get to the proportional over sum over distribution of states multiplied by sum over actions of gradient of policy multiplied by the values of those states. I'm not sure if that helps any me reading these formulas. Probably it's better to go through them, and I can also recommend if that I don't know, maybe you can get an alternative derivation in this lectures from course I mentioned some time ago, the deep reinforcement learning course from UC Berkeley. And yeah, so there is like this, the derivation of the same values, but I don't know, with maybe slightly different step-by-step like a way to arrive at the same value. So I will post a link to that. There are like 2 lectures for policy gradient and actor critic methods that might be a useful complement to this chapter in the book. And yeah, so we got, so what we got here is a gradient of the objective, and it is expressed, so we can see that this is equivalent to expectation under policy pi of this quantity, right? So the sum over sum over states over distribution over states is so this distribution over states is determined by our policy pi, and yeah, so you should remember that mu is a steady state distribution defined by the policy. So that is equivalent to the expectation under policy of this quantity. So this expectation is something that we can sample from and apply stochastic gradient descent or ascent in this case, because we want to maximize the objective. So we will apply stochastic gradient ascent, and that can be done directly by sampling from this distribution, but actually there is a reinforced algorithm that allows us to apply it to sample a single action, a transition associated with a single action, and do the gradient ascent using those samples. So here we will write out, so we kind of multiply and divide by the same quantity here, the pi of a, you can see that the difference here, we multiplied and divided by pi or of a given as sub t. So that is a policy defining a probabilities of actions of from for a particular state as sub t. Then we can essentially observe that a sum over actions under over probabilities of actions is kind of 1 here. So we multiply by 1, which leaves us with this part of the expression, and the q pi of stat is essentially our return from that state. So the in expectation. So the expectation of the return is equal to the q value of that state action pair. Hopefully that makes sense. Okay, and this leaves us with following expression for the update. So now we can basically update using the gradient with respect to particular step sample using our policy pi. And using this, we can get the reinforce algorithm, which can be thought of as a Monte Carlo policy gradient for episodic case. And there are, so this expression here, you can also notice that this is equivalent to the gradient of logarithm of policy. Yeah, so the simple rule here, that a gradient of a logarithm of x is equal to gradient of x divided by x. And the same is true for a function. And in this case, our function is pi. So we will use a logarithm of the policy rather than gradient of a policy divided by policy itself. And that would be useful because we, when combined with softmax, it will give us a simple expression for the resulting gradient. Okay, so, and you can observe the results of applying this algorithm here to this short corridor grid world example. And yeah, you can see that given enough experience and selecting a good learning rate, we can finally converge to something that is close to optimal V star. And you can see a lot of variation here, but remember that the environment itself requires a stochastic policy so we cannot kind of converge very to like a line here. So this variation here is basically expected because of the nature of the environment and the stochastic policy that is required to operate in this environment successfully. But what you can also see here is that the choice of learning rate is really something that we need to make really precisely to succeed. You can see that selecting lower learning rate, we actually never converge to the optimal policy. We get stuck in some kind of minimum, or maybe this is convergent, but really, really slowly, probably. I'm not sure. So also you can see that yeah, it's kind of the numbers here are probably selected to make a point, because here you can see that we start with the less reasonable policy by setting theta to 0 here. Yeah, let me maybe get to the code. Yeah, I should have it somewhere around here. So by selecting the starting value for theta here to be 0, 0, as we usually did in our experiments, we will get something that is already quite close to the optimal policy. So let's just run it and see what would it get us. So basically you can see that by starting with theta equal to 0, we are already quite close to what is optimal policy here in terms of the return. And you can see that basically the plot is dominated by variation. But by making, like, starting from something that is close to epsilon greedy policy with the right action choice, we get a different pattern that is closer to what the authors have in a book, and probably what they've used in a book. They've started with some, judging by the initial values for the reward, they started with something that was going epsilon greedily in opposite direction. So let's see what that would get us, and probably that would be something, but maybe I will have to change a learning rate to make that work, because what I have used here was, oh, okay, so that worked. So learning rates I've used here are quite different from what they proposed in the book. I'm not sure why, so I will need to check the code, the source code used there. But you can see that in my case, the algorithm converges to near optimal solution with much higher learning rate compared to what they report in the book. I don't know, Mayank, do you have another implementation ready to compare? And yeah, I was curious what might be different that makes my results so different from what they have in the book.
I have a plot, just the same, kind of like the same, but
same as in the book, right?
Yep.
All right, so probably a function approximation choice I'm using is a bit different, because you can see that here the learning rate will be multiplied with the gradient, and the gradient depends on how do we select to so the function approximation we select, and yeah, so that impacts. So I was experimenting with some variants here. So you can, instead of going with like softmax and outputting the probability for 2 actions, for this particular task, you can have like a logistic output, and you can basically have a single parameter, but yeah, I haven't quite got through that to make some conclusions, but yeah.
The alpha values you were using were the alpha values I have used to make the figure for are 2e minus 4, 2e minus 5, and 2e minus 3. What were the
okay,
alpha
so
values?
that's the same values I have, but in the book they have like 2 to the negative 13, 2 to the negative 14, and 2 to the negative 12. So okay, so your learning rates are closer to what I have here. So I have like 1 and 2 to the to negative negative 4. So oh, okay. So maybe, yeah, but I will check the source code on the Rich Sutton's website to see what's going on here. Why is that discrepancy? Okay, so anyway, you can see that the algorithm work, but also you can imagine that there is a lot of variance involved here. Because of how unstable this gradient of a policy can be. And let's now consider a way, or maybe should we first discuss the exercises? So here, page 19, the policy gradient theorem. So I haven't done this exercise, and but probably you can find necessary equations in the lectures I've mentioned. So from those deep reinforcement learning course, they have a bunch of policy differentiation variants here. So yeah, and the next exercise, 13.3, we consider policy parameterization using softmax with linear function approx. Okay, with linear for this parameterization proves that the eligibility vector is x of SA minus sum over b. P. Okay, so that can be done relatively easily, but yeah, I don't have that like typed. I went. Yeah, maybe if you, Mayank, want to share the derivations for those exercises, you can share your screen. Otherwise, I guess you might be familiar with this because that is kind of also basic for the supervised learning, and yeah, either way we can either proceed or you can share the derivations maybe.
We can proceed. I don't think so this is required here.
Yeah, cool, but yeah, actually that's basic. So we have this logarithm there, and like the logarithm cancel out. Maybe I will post some link, or I don't know, I can make a photo of what I've done by hand to derive this. Yeah, anyway, that's not particularly interesting. So what is interesting is a way to reduce the variance for this kind of algorithms. So the most basic way to reduce the variance here is to use a baseline, so-called called baseline. And to motivate that, let's imagine an extreme case, and we encountered that multiple times. We often formulate our reward function in a way that on most of the transitions, the reward is 0 and it is positive on the final transition, right? So you can also observe that in that case, for many states, our like G would be also close to 0, and that will make this all gradient update step rather small, right? But what we can change, what we can, and also imagine is that we have some unit discount factor. In that case, basically the final state reward can decay to 0 for some states, and that would make some updates just like zeroed out in general, right? And that is like an extreme case to demonstrate the high variance associated with the policy gradient update. Otherwise, so basically it kind of depends on this Q value associated with particular state. But what we can do, we can subtract a constant or any value that does not depend on action from Q here, and we can show that the expectation of any function of a state, so here we have this function B, which stands for baseline. So this depends on a state, but does not depend on action. And we can show that the expectation of this value will be 0, because if it does not depend on action, we can take it out from the gradient here. So we will have a gradient. So the gradient of a sum is a sum of a gradients. That also, and we use this to simple rules from calculus to show that basically what we get the product of B of S with a gradient of a constant, which is 1, sum over all actions of a policy, which is 1 by definition, and that would be 0. So we subtract some, so we can safely subtract something that is 0 in expectation, so that will not affect the expectation to which we are had the expectation of the update, but it will affect the variance of the update. And by selecting smartly this baseline, we can improve the performance of the reinforced algorithm. And a reasonable choice for the baseline would be just an average value of that state, right? So I guess that makes sense. And here in the box, in the box here, you can see how we can use a value function, which in this case, it basically is used to learn the expected value of each state. And we can use that to improve our policy gradient algorithm here. And you can see that in this case, we will use this delta, which denotes the difference between the observed return. So this is our sample, empirical experience with the expected value of that state as we learned so far. And yeah, so here it's demonstrated that this speeds up the convergence quite significantly. And that is mentioned that now we have to select two hyperparameters, but essentially the choice of hyperparameter for alpha W is relatively easy. And as it was mentioned in the chapter where we introduced value function approximation with learning value function with function approximation, that can be, there are heuristics you can use to select the learning rate for W, which is a parameter vector for our value function. And by doing so, we can kind of improve the convergence of our learning algorithm, but also note that this is not an optimal baseline, and the optimal baseline, yeah, let me quickly get to that. Optimal baseline, we can basically analytically derive a value that minimizes of a baseline that minimizes variance, and that would be that would depend on the parameters, but so yeah, we will weight it by the gradient, the magnitudes of the gradient, but this is not done in practice often because it's kind of complicates things way too much. And using the like as we did, using the estimate of value for a particular state is often a good choice for a baseline. But yeah, you can dive into the details and see why this derivation makes sense. So, and how we can kind of minimize, select a baseline that minimizes a variance of the objective. So that's just an interesting thing to look at. Okay, so that's that is a way to reduce the variance, and more is discussed in those lectures I mentioned. But now let's move on to actor critic method. So here, when discussing reinforce with baseline, we saw that we can use estimate of values of the states to improve our reinforce algorithm. Can we go even further in this direction and make essentially what would be a hybrid of the algorithm we that estimate like value function and a policy gradient algorithm. So now we come to what is called actor critic methods, where actor stands for the policy function and critic stands for the value function. So here, let's just dive into it by going through this actor critic one-step actor critic episodic algorithm. So again, we have both two differentiable functions here, parameterized policy function parameterized by theta, and state value function parameterized by W. We have two learning rate parameters for two of the parameter vectors we have. And yeah, so again, we go through the episodes. We start from some state, and we have this value I, which we initialize to 1. Then we just very similar to reinforce, we iterate over states. Then we use this. So remember, before we used a complete return G to compute this value for delta. But what we do now, we use this bootstrapping approach, familiar bootstrapping approach. We can estimate G as reward plus gamma multiplied by the our value estimate for the next state. So that's what was introduced in TD methods, right? So now we will use this to update our theta parameter vector, as well as W, right? And that allows us to combine bootstrapping and the policy gradient. And essentially, as you remember, bootstrapping, it does reduce the variance even further and speeds up early learning, but it also can introduce some bias. So the baseline, which we discussed before, it does not introduce any bias. So this line here, it shows that the expectation of the change in the expectation is 0. But it's not the case for the bootstrapping. But again, in practice, bootstrapping often has its benefits in reducing the variance and speeding up the learning process. And we can naturally go on to extend this algorithm. So you saw that the actual change from to get from reinforced to actor critic method was minor. So we changed the way we estimate this delta, which is used to update our parameter vector, and that change is very similar to what we have done to get from Monte Carlo to the temporal difference learning. And as with Monte Carlo and temporal difference learning, what we can do, we can use eligibility traces as well as n-step bootstrapping to improve this algorithm even further, to give it a bit more, even more flexibility by making this like bootstrapping from multiple states. And here we have this eligibility traces algorithm that is like the most probably most useful algorithm from all those, which is like complete backward view eligibility trace algorithm. So it does not require any like delaying the update by any number of steps, but also allows us to use this n-step bootstrapping through eligibility traces. Here you can see that we will have to have two vectors for the eligibility trace, both for theta and w. And here you can see the formulas we use to update those eligibility trace algorithms. Those are essentially very similar to the ones introduced in the previous chapter. And again, the update is similar to what we have introduced in the previous, what we have observed in the previous chapter. So yeah, so that's the way to combine the bootstrapping and policy gradient using eligibility traces, and that's like actor critic with eligibility traces algorithm for episodic task. Yeah, if anyone wants to jump in and discuss anything regarding this, yeah, please go on. Otherwise, we can continue to the policy gradient for continuing problems. So yeah, so far we discussed the episodic case, and that was kind of useful simplification. We had that idea that our task will eventually end, and we can use the complete return to update our parameters. But we can apply the policy gradient to continuing task. And for that, we will use the average rate of reward formulation that was introduced in chapter 10. And here we can, so to do that, we will introduce a new objective, right? Our previous objective function was the reward from the initial state up, and that was relying on the idea that we have this notion of episodes that start in a certain state and then proceed to termination. But in continuing task, it is more useful to formulate the objective as an average reward rate when following some policy pi. And that would be, so here we have some time horizon, and we take the limit where as time horizon approaches infinity of the expectation of a reward starting from state as 0 and yeah, up to that kind of horizon, right? And all that divided by the number of steps. So that would make the expectation of the reward starting with that state, right? So that this can be rewritten as a sum over all possible over distributions over state multiplied by the sum of distribution over actions. So then we multiply it by sum by the product of the reward multiplied by the transition probabilities, right? So that is kind of basic that is the same kind of quantity or written in different manners. And yeah, so the mu is a steady state distribution that we have it as we select the action according to the policy, we remain in the same distribution. That was probably introduced in chapter 10 or 9, and we discussed it as well. And by rewriting this objective in the following way, we can now produce an actor-critic algorithm with eligibility traces for this case. So now what will change in practice? In practice, we will have to keep track of this average reward, and we will rewrite our delta. Now it instead of having this discount factor here, we will subtract an average reward from the current reward, and we will just use this kind of update. We will have another learning rate to update our average reward to make sure that it is representative of what we observed so far. And otherwise, everything is similar to the actor-critic with eligibility traces for episodic case. So the change is in this line here, that we change how we compute delta, plus we add the update for average reward that we need to compute this delta. Okay, and you can go through the proof for the policy gradient theorem for continuing case. So it's applicable for continuing case as well. Yes. So and in this case, the complete return is kind of sum of all the returns minus the average of all the rewards minus average reward. So that's the return for that case. All right, so that's kind of might be a bit math heavy, but if you think about it, it's a natural extension of what we had learned so far. Now, now we get to the fact that we can use like one benefit of the policy using the policy gradient is that we have this policy. So what our what our function outputs is some parameterization for the policy, and before we discussed that the parameterization would, the function will output some logits that we will then feed to softmax and get the probabilities of the actions. But we can also apply a different parameterization and use that with continuous actions rather than discrete actions. So you might kind of remember that it is quite it's not obvious how do we apply, for example, that value function based method for the case when we have a continuous action space, because it's not trivial to learn the action value function. It might be not trivial to learn action value function in that case. What we can do with parameterized policy, we can have this idea that we essentially output the parameterization for some distribution as a we have a parameterization of distribution as output of our function approximator. And for example, we can use a simple Gaussian distribution as a distribution over action, and we can what we can have as an output, some we will need to output a vector like a means and the standard deviation for that distribution. And yeah, here you can see some bell-shaped, familiar bell-shaped curves that correspond to different means and variances parameterizing the Gaussian distribution. So in this case, our mu and sigma will become a function of theta. And yeah, essentially, I think it's really like a simple to imagine some neural network that outputs mu and sigma for a distribution, and that then we can use that to parameterize a Gaussian and sample from it. Yeah, that's quite straightforward. So you can see that one of the simplest way to do that is using a linear function approximation, and in that case we will just have some feature vector for mu's and feature vectors for sigma, and then a parameter vector for mu's and sigma. Also, we like it's this linear function approximator, it will output the full range of real numbers, but we want sigma to be a positive number, and we can achieve that by applying exponential to that. So essentially, you can think of it as outputting logarithm of the variance rather than the variance itself. So yeah. And for that, you can see that here is a way to express the corresponding gradients. And I guess yeah, so it's asked that we derive these expressions here, but you can probably observe that, yeah, that should be quite straightforward given this expression for parameters for like Gaussian distribution, and the fact that we are using linear function approximation. Yeah. All right, so that concludes the chapter, and yeah, so as a summary, we can, the authors mentioned that methods that learn and store a policy parameter have many advantages. So they can learn specific probabilities for taking action rather than just preferences over actions as we had for action value functions. Yeah, so we can also learn the, so the exploration is very different in this case, because we can output this probabilities over action, and so rather than having having to stick to the epsilon greedy for policy for exploration, we can basically approach the deterministic policies asymptotically while using the policy parameter approximation. And in some cases, it is just simpler to learn policy directly than trying to approximate the value function. So essentially, for different kind of environments, it can be the case that a policy can be easier to learn, or a value function can be easier to learn. And basically, you can switch between those two choices to make sure you use the most appropriate method for your particular task. And we also have discussed the actor-critic methods that kind of introduces the way to use a value function to improve the learning abilities of the algorithm. So that's basically the end of the chapter, and I highly recommend those two lectures. I will post the link to those as a complementary to this chapter, as I kind of go to a bit more details, probably because the policy gradient methods are more relevant for deeper reinforcement learning compared to shallow reinforcement learning, because you can have like a more expressive policy function, and essentially that can be useful in many cases, I guess. Yeah, and also there are a lot of stuff we haven't really dive into, like different improvements over this algorithm, further improvements like natural gradients, and yeah, there is a fact that with some trust region optimization, by making sure that your policy does not change too much between steps, you can view the policy gradient method as a particular case of policy iteration. And you can remember that we had this, the policy iteration is basically in the core of many algorithms we discussed. And it has some nice convergence guarantees. And by applying certain modifications to make sure that the policy does not change much between steps, we can basically apply those guarantees for policy gradient methods. So yeah, that concludes this chapter, and I guess that concludes the part of the book that deals with function approximation methods, and we will proceed with this part 3 of the book, which talks about some psychology and neuroscience intuitions behind reinforcement learning, and also that presents some successful applications of reinforcement learning ideas to interesting tasks, as well as introduces us to some of the cutting edge research questions present in the reinforcement learning field as of today. All right, I guess that's all I have to say about policy gradient methods, and let's proceed with discussion or of policy gradient methods, or of any topic we would like to discuss.
Thanks, Arthur. That was great.
Yeah, any progress on the Flatland challenge or maybe other challenges? I've honestly haven't made much myself, but if anyone has something new to tell about those challenges, please go on.
I haven't really got to do anything on it this week. Last week I'd sort of looked into it a bit, but I find it quite difficult sort of taking the theory that's in something in Bardo's book and applying it to real life. So like a while back I'd sort of published it, put the link up on Slack to the other book, which is more practical based. So I've been working through it a wee bit, just playing about. It does like a lot with the Atari games. So I've been playing with, like the Pong game, where it's using like a deep Q network to play with that. So I was hoping to apply that onto Flatland. Flatland itself, though, it's a bit different from other things because of the fact it's like multi-agents. So you're not just dealing with sort of one thing getting a reward, you're dealing with like a lot of things at once, moving about and interacting. So yeah, I need to look into it a bit more. There's another Kaggle competition that's just launched at the minute, which is like predicting cryptocurrencies. And I know you can use like reinforcement learning to predict movements in sort of financial markets or whatever. So I was going to look at that as well.
Yeah, that sounds intriguing. Maybe, maybe we can kind of prepare some case studies for the next session. I don't know. There are kind of bunch of options. I think it's a good idea to start with a simple scenarios, like as you said, applying this theory directly to some tasks can be not as straightforward as we would want, maybe, and still we haven't in this book we haven't got to deal much with deep reinforcement learning, which is probably what is of interest currently. So it will be interesting for me to have a look at any like this either Atari game solved with reinforcement learning, maybe some comparison of algorithms and stuff like that. So I'm not sure how to like really incorporate this into the flow of our study group, but I'm sure we can make it up somehow. And we completed the practical like most like basics of reinforcement learning, and that should definitely give us a good basis for understanding like more state-of-the-art approaches to different tasks. So hopefully we will go with that. And I guess anyway, we shall proceed with this looking deeper chapters because a lot of interesting ideas should be discovered there. Also, I was kind of thinking about this tile coding, essentially, and the benefits it provides. So I found it interesting that Rich Sutton is kind of bound to this tile coding idea in our like times of deep reinforcement learning and stuff. But on the other hand, this tile coding actually provide us sparse representation, and maybe it is kind of a shallow way to get the sparse representation, but you can also think of maybe using some more a complicated technique, for example, a neural network to provide you an encoding, and but it is also appealing to have this ability to apply some simple function on top of a sparse representation to get the result. So yeah, I find it interesting to maybe explore that idea a bit further, and yeah, I think there are perspectives in that. So yeah.
Okay, thanks very much for that, Ardo. I need to drop off now, so I'll catch you all later. So speak to you then.
Yeah, thank you for joining, and I see you.
Cheers, bye.
I think so. We should end the meeting too. If we have nothing else to add, I think so. We shall continue with the psychology part next time.
Yeah.
Okay. Okay then. Thanks everyone.
Right. So see you next time.
Thank you.